Okay, welcome everyone to the last seminar, SIP seminar of the semester, and it's a pleasure to have Professor Salman Avestimehr join us from University of Southern California. Salman is going to give us a talk on coded computing, a transformative framework for resilient, secure, and private distributed learning. Before I hand it over to Salman, let me just tell you a little bit, although he doesn't need an introduction, he's known to most of us, but he received his PhD in 2008 from Berkeley. He's currently a faculty at University of Southern California. He's a fellow of the IEEE, and he has won a number of awards, including the James Massey Research and Teaching Award from IT Society, the Presidential Early Career Award from President Obama, Young Investigator Award from United States Air Force Office of Scientific Research, an NSF Career Award, and David Sacrison Memorial Prize, as well as the Information Theory Society and Communication Society Joint Paper Award. And the list can go on, so I'll stop here and hand it over to Salman for an exciting talk. And as always, if you have questions, please either unmute yourself and feel free to ask, or write it in the chat and we'll communicate that to Salman. So with that, I'll hand it over. Salman, all yours. Thank you.
Hi, everyone. Thanks, Wahid, for the nice introduction. Glad to see you all virtually. I'm trying to figure out how I can minimize my Zoom thing so I can see my slides. Okay, I figured that out. All right, so as Wahid mentioned, maybe we can make this interactive, because typically, one danger of virtual talks is the speaker thinks he's alone in the room and doesn't get any feedback. And you guys would think I'm just a video. I'm not a video, I'm a person here. So if, at any time you could, ask questions or anything was unclear, I think that would be very good for me. Okay, so this talk, as Wahid mentioned, is about coded computing. This is a research area that we have been working on in the past couple of years. And for today, I'm gonna, in my talk, I'm going to have two parts. The first part discussing what coded computing is, and the second part, applications of it for, in federated learning and machine learning. This work is in collaboration with quite a few people, students, postdocs, colleagues that I have listed here. There is one person, Tian Yu. He's going to be in the market this year. I don't think you guys have positions, but if you're looking for hiring, I fully recommend him. All right, so let's start. Maybe I try to motivate the problem setting by two scenarios, okay? Just 1 second. All right. So the first scenario is, let's say you are a client and your data set is stored over the cloud. For example, your data set typically, is going to be stored distributedly across the cloud. Let's call them X1 through XK. And you want to leverage the cloud for your computations. For example, maybe this is your data set. Over your data set, you want to do a training and you want to compute the maybe gradient calculation over each of those pieces of the data set. Or maybe it's an inference. You want to have your data set and then you're looking for some inference. You want to figure out whether a specific person is in your images databases or your video databases, etc. Or maybe this is just a usual cloud computing application. Okay, so in this case, X1 through XK is the data set. You are interested in the computations F over your data set. Then typical challenges is, that I'm interested in is, what if some of these nodes straggle or fail? Okay, so typically a straggler or failure is a common thing that you would see over the cloud. And, in Amazon Cloud, Google Cloud, anywhere you use it, these nodes, although they have the data set, for some reason they may run slow for giving you the computation results. And that's a big challenge for many data companies, even if it's their own dedicated cloud. For example, if you look at the Facebook application, typically over the data set, the type of computations Facebook need to do is deciding as you are scrolling down through your Facebook page, what advertisement to show as you are going down. Okay, so that's the computation that needs to be done over your data set, like your past history over the cloud. And there is a latency requirement because they have to make those decisions in a couple of milliseconds. Otherwise, there is money that is lost. There is advertisement money that is lost. Okay, so if you want to minimize the impact of failures or stragglers, a straggler means a node who is running slow, you have to make or you have to run these computations fast. Another part would be maybe there is going to be some malicious nodes that they try to give you wrong results of the computations. Okay, so for example, you want to figure something out in your cloud, but this node is hacked and it may give you a wrong computation result. And a third part is that what if you want to use the cloud, but you don't trust the cloud? So you want to make sure that you keep your data private to each cloud node or a fraction of them that collude. So the question is, what are you going to do? Okay, so that's one motivating scenario. The other motivating scenario is the dual of these, which is like related to federated learning. And the idea is that now the data set, as opposed to being over the cloud, is across distributed users. Okay, so there are maybe end users, a bunch of Alexa devices, a bunch of iPhones, and every person has his or her own data set. And you want to do machine learning across massive amount of data that is collected distributedly at the users. And again, you could ask the same questions. Yes, they want to collaborate with each other, but it's very likely that some of the nodes may not participate because they go on a call and they cannot participate in one round of learning, or they may just run slow because they have to do other things, so they cannot participate in the learning effectively. In this case, I think the issue of being malicious is obvious, means that these are distributed nodes and one node may just decide to influence the training into his or her own benefit, right? So maybe in the cloud, you would say, maybe I already trust the cloud. There is no security issue. But here is obvious. I mean, any node could become a bad node. And at the same time, while you want to collaborate, this is your own private images or your own private transaction history. You don't want other nodes to learn about that. So you want to maintain the privacy and you want to make sure that whoever is facilitating this federated learning, the cloud, for example, Google Cloud or Amazon Cloud, is not learning about your personal data. Okay, so that's what I'm after. How to get resiliency, security, and privacy in distributed computing, either in federated learning or distributed cloud computing. All right, so as you can imagine, this is a problem that many people have looked at it or are looking at it right now. So it's an active area of research. And typical method to deal with failures and malicious behavior is by computation replication, meaning that if there is one node who is running slow over the cloud, you try to quickly replace it with another node or by replicating that computation. The same thing for malicious behavior. You try to come up with more redundancy so that you can figure out the outliers and throw them away. And if you want to do private computing, then there are different methods that people are working on. For example, we have Professor Sarwate in the call, Anand. He would champion differential privacy. I don't know whether we have on the Zoom call colleagues who are expert on homomorphic encryption. Somebody would say, I'm going to use homomorphic encryption. Or if you have CS crypto people or in general crypto people, somebody would say, I'm going to use secure multi-party computing for the last two bullets. Okay, so this is essentially the suite of approaches that you may have for approaching this problem. I'm not gonna propose these methods, although they are good methods. Instead, I'm championing a different approach, which is our proposal called coded computing. Okay, so it's kind of a different approach, and as I will go through the talk, is going to provide a lot of benefits compared to these conventional approaches or these other approaches for solving resiliency, security, and privacy in distributed learning. Okay, so first, why is it called coded computing? The reason is that coded computing is merging two ideas from two domains. The first one is coding theory and information theory, and the other one is computing theory, and that's why we call this area coded computing. And the motivation that we tried to work on coded computing was, if you think about resiliency, security, and privacy, these are also the same issues that you would have in communication systems. Okay, so right now we are all using cell phones, using internet, and of course it is resilient, it is secure, and it's private. It means that when I send my images, nobody in the middle in the internet can figure out what those images are unless the intended receiver. And at a high level, this is solved by using a channel and data encoder and a decoder. Okay, so it's kind of a black box approach that is used for solving this through encoder and a decoder. The idea of coded computing is, why not bring the same concept to a computing system? So a computing system, you have an input, you have an output, and you have some processing node. Why not just have now, instead of a data encoder, a computation encoder and computation decoder that will give you the resiliency, security, and privacy that you want to have? Okay, so that's the high-level goal of coded computing, an approach similar to communication systems that via a computation encoder and computation decoder gives you the three things that we want: resiliency, security, and privacy. All right.
Can I ask a question?
Yeah, of course.
So I think I have some idea about like how information theory and coding theory works here, right? And but something it's less clear for me is what is computing theory. And so basically in this diagram, we have some encoder, decoder, which are information theory and coding theory stuff.
Mm-hmm.
But where is computing theory?
Excellent question. To answer that, maybe we should have a compute model so that I can talk about that, right? So that's why this is more of, so far is cartoon, right? Means that a cartoon description of what coded computing is and how it sits in a system. Okay, so imagine, for example, this computing point is going to be a cloud, and the idea is that before you send your computations to the cloud, you want to pass it through a box, which is a computation encoder, and then before recovering the result, you will pass it through another box, which is a computation decoder. Okay, so this is more of a system diagram. But my plan is in the first part to tell you what is really coded computing. Okay, so you're asking the right question. I haven't told you yet.
Okay, thanks.
Sure. All right, so what is coded computing? Hopefully we know in a system diagram what is it that it should do. So let me start again with a little bit more cartoon before I tell you the meat of coded computing. So at a high level, let's say if I want to explain coded computing in a nutshell, it would be, let's say you have two computations. Okay, so you want to compute f of x1 and f of x2. And let's say for now, focus on resiliency, and you are worried that one of these computations may be dropped. Then in a replication approach, what you would do is you have to replicate each computation another time so that as long as there is one failure in the system, still you can recover both computation results. Okay. Now, the idea of coded computing is, can I replace these two replicated computations with one coded computation? Coded computation would mean that you're going to code your data and you compute over coded data. Okay, so that's why it's called coded computations. Computations on a coded data. Note that if it was just a data storage problem, and your goal was to recover x1 and x2, simply this coded version could have been x1 XOR x2. Okay, so like a parity would have solved the problem. But now the issue is that you are doing computations on the data. All right, so that's what coded computing wants to do. How would I create the concept of parity on the computations? Okay. As you can imagine, the key challenge is that how would I code the data so that when you compute on it, you get something that is meaningful? Okay, so meaningful is a little bit vague term, but as I go through the talk, we understand, and maybe the magic of coded computing is really to understand what computations are meaningful in the sense that you can use them to recover the result that you are interested in. Now, why is there hope even to have a coded computations? This field started by the hope in the special case of linear functions. Okay, so linear computations where f is a linear computation on the x. Okay, and it was started by using MDS coding, by Lee et al., short dots, etc. And this special case is interesting because in that case, coding, linear coding and computation would commute. Means that if I encode my data using a parity, the same as before, computation on the coded data becomes a coded version of the computations. Okay, so means if you just create a parity of the data and you compute on it, you get a parity for the computations. So since the two commute, for linear functions, any linear code, you can use it and you would get automatically parity for the computations. But this is just a special case, although linear functions are important, but most computations of interest are not linear. And what we have been working on is how to design coded computing for general class of computations. Okay, so that's why I put the word meaningful here. You could have put, how would I design code so that computations and coding would commute? That would have been like an obvious way of designing coded computing. And actually, that was a problem that was studied a decade ago, okay, in the context of fault-tolerant computing. And it turned out, you cannot hope for having this property of commutability for any large class of computations beyond linear functions. And that's why nobody was able to come up with, the design for more general class of computations. That's why our goal is to change that word instead of hoping for commutability to get something that is meaningful. Now, if you're also familiar with homomorphic encryption, there is also some resemblance there. In homomorphic encryption, you want computation and encryption to commute. Okay, here in the context of linear codes, the computations and coding would commute. All right, so how would I do that? How would I design coded computing for a general class of computations? The first class of nonlinear computations that is of interest is bilinear computations, and that would be matrix multiplication. Okay, so this is bilinear in both A and B. And this is like a building block for a lot of data science applications, machine learning applications, and typically the matrices that you want to multiply are massive in size, so you have to do it distributed. Okay, so let's say you want to do it distributedly across 4 machines, and one way you can do it is chop A to 2 parts, chop B to 2 parts, and then if you have 4 machines, okay, each machine could give you the result of the computation for each component. So let me go back again. Remember, you had to multiply A by B. I broke A to A0, A1, B to B0, B1. Now I have to recover A0 times B0, A0 times B1, A1 times B0, and A1 times B1. And if you want to do it distributedly, you use 4 machines. The first machine has A0 and B0, multiplies them. The other one A0 and B1, A1 and B0, and A1 and B1. Okay, so as I mentioned, let's start by focusing on the resiliency part, the security and privacy. I will talk about them later. So let's say now you have one failure. One of these machines could run slow or be failed. If you want to do replication, then each computation you have to replicate it twice. This would mean you have to use 8 machines so that, or 8 computation units, so that you can tolerate only one straggler. Okay, so that's what you would get with replication. The idea is, could I now use coded computing? Could I design coded computing to do much better? Just to put it in perspective, if you have 100 computations, to just tolerate one failure, you have to use 200 machines. So it's a very inefficient way of dealing with failures or creating resiliency in the system. So can we do better? So the first one is our first code, polynomial codes. And the idea is as follows. So remember, I'm going to encode my data first. And I'm going to use a different encoding for A matrix than B matrix. Okay, so I'm going to use a polynomial f for encoding matrix A, which is given by this polynomial, A0 plus A1x, and another polynomial G for encoding matrix B. These are special designs, and in a couple of minutes, it's going to be clear why these are good designs. Okay, but nevertheless, I encode the data. And what each server, remember I had 8 servers, what each server is going to do is going to get the coded version at point I. Server I is going to get f of I and g of I, and multiply them together the same as before. So a black box approach that I was telling you earlier. So what it would mean is my 8 servers, for example, server 1 is getting f of 1 and g of 1, which is A0 plus A1, B0 plus B1. It doesn't know what those are, just multiplies them together. Server 2 is getting f of 2, which is A0 plus 2 times A1, B0 plus 4 times B1. And by the way, these A0, A1, etc. are big matrices. And when I put 2, like 4, this is just a scalar multiplied by the matrix. Everything for now assume is finite field. There is no wraparound. Okay, and multiplies them together. Now let's see what would happen. Okay, so each server X is getting encoded data and does the computation, which is multiplication on the encoded data. Means multiplies f of x by g of x. So let's see what is the computation that each machine is getting. And remember, my goal was I wanted to make sure the computations on these coded versions are meaningful. So if I expand that, is going to be this. So this is the computation that server X is doing, is calculating this. And if you look at it a little bit, you would see an interesting property. These polynomials were designed in a manner that when I multiplied them together, no two monomials had the same degree of X. So it's kind of, they got all spread around. The only degree 0, 1 was A0, B0. The only degree 1 was A1, B0, etc. That's why I designed it this way. And more importantly, if you recall, the goal of computations was to recover these 4 parts. These 4 parts are now appearing as the coefficients of this polynomial h. Okay. So what it would mean is that the meaning of the computation of each worker is evaluating a polynomial that has the desired computations as its coefficient. Okay. So remember, our goal was matrix multiplication. Through this coded computing, this polynomial codes approach, what each machine is doing is calculating a polynomial that has the result of the computations as the coefficient of that polynomial. So now all of a sudden, my computation problem transforms into polynomial recovery or polynomial interpolation, meaning that my goal is to recover the coefficients of the polynomial h. these 4 parts, because if I recover them, I know all the 4 components that I need. Now, h of x is a degree 3 polynomial. Each node is evaluating a point on that polynomial. How many evaluations would I need to recover h? I would need 4 evaluations, because any degree 3 polynomial, you can recover it if I give you 4 points on that polynomial. Meaning that the result of any 4 out of those 8 servers is enough to recover the matrix multiplication problem that we had. What does it mean? It means if I'm using 8 workers, now instead of tolerating 1 straggler, I can tolerate 4 times more straggler. Huge gain by coded computing.
Can I ask a quick question, Salman? So, but is that gain coming at the expense of also additional computations per server? It seems
Very good.
that each server is doing more computations than before.
Excellent. So remember, each server is doing exact same amount of computation as the uncoded approach. The size of A0 and the coded version of it is the same. Means that when I encode them, the size doesn't change.
Oh, okay.
Okay, so the computation at each machine, there is no cheating here, is exact same amount as uncoded. But remember, in the block diagram that we had at the beginning, there was a computation encoder and a computation decoder. This part is unchanged. I encoded A and B, gave them to the machine, they multiplied them, right? Now, you're asking a good question, then what is the complexity of these 2 blocks? Because I have to encode them manually and give them to the machines, right? So the encoding part is simple because it's linear, right? So there is not much complexity of the encoding compared to, you have to always compare it with your matrix multiplication. So matrix multiplication, the complexity of it is more than quadratic, right? Like typical algorithms like cubic is the obvious one. But if you use, maybe better algorithms, you can do like n to the 2.7, kind of 2.5, whatever. So it's more than quadratic. This is linear, means my encoding cost is negligible compared to the computation cost. For this last part, if I get the result of 4 servers, I have to recover the polynomial. So I have to do a polynomial interpolation, right? The good news is that problem also you can solve it if the size of the matrix is n by n, you can solve it as n log n. Okay. The way you would do it is like there are fast polynomial interpolation approaches that convert this problem to FFT approaches. So in other words, the complexity of my encoding and decoding is negligible compared to the computation that each server is doing. This is something that I have to do before I give the works to the servers and get the results back.
Can I ask a quick question?
Yes.
So this has a flavor of Reed-Solomon codes.
Definitely.
Can you divide more and push this further? What's the limit?
Excellent. So what is the connection? I'm glad you asked. So you see, in Reed-Solomon code, you are in the last step. Remember, you have your data set ready, right? And you encode your data set by passing a polynomial. So this would be my data set, by passing a polynomial through that, right? Here, you don't have your luxury. There is no data set. The question is, how would I encode the data so that after each machine is computing, is getting a Reed-Solomon code that is passing through the computation results? Yeah. So means, what is Reed-Solomon code? You have a data set, you pass a polynomial through it. Here, I don't have these computation results. That's the whole challenge. So I cannot just pass a polynomial through it. The magic of polynomial codes is that after the computations, the computation of each node looks like a Reed-Solomon code that is passing through the computation results. So that's a connection. But it's not like you're applying Reed-Solomon code here, right? Because you don't know these parts.
Excuse me. What about doing this for the reals, and in particular numerical stability?
Excellent question. I never used any assumption on finite field, right? Where did I use that? Polynomial interpolation that I talked about could work for reals. What you're asking about is if you want to interpolate a polynomial, right, you should be careful for numerical stability, meaning that what are the x's that you should choose, like the points on the polynomial, right? And typically, if in finite field, there is no distinction between what x's to choose for when you give the computations, like it could be 1, 2, 3, 4, there is no difference. In reals, these points matter. And typically you want to have so that your inversion problem is, a good inversion problem. One approach is through van der Monde matrices. Nevertheless, we have analog coded computing. Like there is a paper that we have, and you can take a look on how to deal with these issues. But that's a very good question. And the trick is how to choose my points of evaluation. Okay?
Yeah, thanks.
Sure. All right. So matrix multiplication, hopefully I gave you the idea. The whole thing would generalize. Let me quickly go through a more general class of computations. The state of the art on coded computing is that we can now design it for any polynomial computation, means that any f that could be written as a multivariate polynomial in the data set. So this would capture all the matrix algebra, tensor algebra, typical data processing like filtering, and some loss functions in ML, which you can model them as polynomial loss functions. So how do we do that? The coding to use there, we call it Lagrange coded computing, and is given by this data encoding. Okay, this is a lot of math, don't read it. So this is how my encoding now would look like for a general polynomial computation. The idea is as follows. You have your, remember, data set x1 through xk. Okay. What you would do is you pass a Lagrange polynomial through your data set that at beta 1, beta 2, and beta k is going through your data set x1 through xk. Let's call that the blue polynomial u. Now, what each worker is getting a point on that polynomial. These red points means the evaluation of that polynomial at alpha 1, alpha 2, alpha n. Okay, so that's how my Lagrange coding would look like. Now, after each point, each server, like I have n server, each server is getting a point at u of alpha I, is gonna do the computation on the encoded data the same as before. Okay. Now, once it does the computation, all the computations of the workers would be on another polynomial, a green polynomial h, and this polynomial has a very specific property. The first property is that the degree of this polynomial, what is it going to be? The degree of the polynomial is k minus 1, where k is the number of data sets that I have, because to pass a polynomial through k points, the degree would be k minus 1. Now, if I compute over that, f of u of z, that would be the degree of this green polynomial is degree of u, which is k minus 1, times the degree of computation, which is degree of f. Okay, so any machine is finding a point on the green polynomial, and the important thing is this green polynomial is going through the computation results that we are after, f of x1 through f of xk. The reason is at each beta I, at beta 1, u of beta 1 was x1. So if I know where this green polynomial is going at beta 1, I would get f of x1. If I know where it's going at beta k, I got f of xk. So I get the same property as before. Means by Lagrange coding, now each worker is computing a point on a green polynomial that is going through the computation results. So again, my problem is mapped to the same problem of recovering or interpolating a polynomial. Since I know the degree of the green polynomial. I would only need the result of degree of the green one, degree of h, plus one node to figure out how many workers do I need to wait for so that I can recover the computation results. Now remember, the degree of h was k minus 1, the number of data sets or number of computations that I need to do times degree of f. So now the number of points that I would need would be k minus 1 degree of f plus 1 workers. If I have that, I can recover all the computations, and the rest of them, I can tolerate them as stragglers. Okay, so that's a general approach for solving the problem for any polynomial computations. You pass a polynomial through your data set. The nodes compute on the encoded data the same as before. Once you get enough results, you would interpolate the polynomial and figure out your computation results. The magic is the same as before. By this coded computing, each node, the computation of each node is giving you a point on a polynomial that is going through computation results. A couple of points about this, encoding. First of all, this encoding, when I'm doing my encoding, I never worried what computation you wanted to do, so it's oblivious to any F computations that you wanted to do. And that's why I was saying we are looking for black box approaches, meaning that when you are encoding your data set, it can be used for any computation that you wish, any polynomial computation. You don't need to change it if later you want to do a different training. Maybe today you want to train one model, tomorrow train another model, etc. And the other part is this is incremental, meaning that maybe these data sets keep growing because maybe you store or you collect more data, you capture more images on your phone, etc. Since encoding, if you look at it here, is going to be vector encoding, you can just amend the coded version at the end of each data set and just encode the last part. So it's incremental, which is also an important feature because your data is stored over the cloud and also the coded version. As you get more data, you don't want to re-encode all the other previous parts. So you also get these two key properties for free. So what do we get? We get the first result, meaning that if there are k computations you want to do, you have n machines. You need to wait for k minus 1 times degree of your computation plus 1 machines to recover the result of your computations. Meaning that the remaining n minus t star, you can tolerate them as failure. Something to note is the number of machines you have to wait for is a fixed number. Okay. What it would mean is that as I add more and more machines, for any more worker that I add over the cloud, I can tolerate one more failure. This is like the optimal scaling that you have in data storage and data communication. We are providing the same scaling for distributed computing. Any one extra computation gives you one extra robustness to failure or delay. That's the best that you can hope for. All right, so then you would say,
question?
Yeah.
So here, this threshold is scaling linearly with k, right?
Right. Yeah.
And k is your input data blocks. So what is a data block? Is it like a subset of your data set, or is just one point in the data set?
Excellent.
Because
Very
this
good
can go very high, right?
Excellent. So K is view it as how much parallelization you want to have. Okay. So meaning K is really, as you mentioned, is not written in a stone, is a design parameter too. So remember, you have a huge data set X, you are breaking it to K parts. The larger the K means the amount of computation per worker is going to be less, means more parallelization. Think about, for example, these K parts are your mini batches of the data, like different batches, right? So the question is, what is fixed here? So there are two ways. Maybe one way is you say, I have decided I have only access to 100 workers in my lab. Okay, so we fix n. Then k is your choice. By making k larger and larger, the computation per node gets smaller and smaller because every node is getting a smaller batch. But your resiliency goes lower and lower too, because the larger the k, you have to wait for more workers. In the extreme that k is equal to n, you cannot tolerate any failure. The lower you make your k, then you can tolerate more stragglers. So this you can view it as a trade-off between k and how much straggler toleration can you have. The way I put it is trade-off between parallelization and resiliency.
And do we know what the optimum k is? Like, do we have a guess?
Very good. So that depends on your setting. In the case of a straggler toleration, maybe in your system you don't have any straggler, then maybe you just want to make sure you have only 1 or 2 failure, you put k large. Okay, so the question is, how much resiliency do you want to have? Based on that, you can design the optimal k.
Okay, thank you.
Or if you have maybe some tail latency, like how much tail latency do you want to tolerate? So that's a trade-off you would have. All right, so we focused a lot on the failures. I mentioned you can use it for security, you can use it for privacy. Let's say, what if you have now some malicious nodes that can give you wrong results? Well, nothing changes, because now there are some nodes that are telling you points that are not on the polynomial. Previously, I assumed every node is giving you a point on the polynomial. That's how we got that. So now the question is, if you have some nodes, n nodes, that some of them may give you a point wrongfully, not on the polynomial, how many of them do you need to wait? Well, for any a adversarial nodes, you need to wait for 2 times a more machines. That's our theorem there. What it would mean is that now each additional worker can create resiliency to adversarial nodes by 1/2. Means that if you want to tolerate 1 more adversary, you need to add 2 more machines or 2 computation points units to the system.
So Salman, quick question. When you use for adversaries, they're allowed to send anything?
Anything, yeah.
Okay.
And again, this is like the optimal scaling you have for data storage and communication. Means for any error, you need 2 parities to correct for that. We are getting the same optimal scaling for computations. And finally, what if you wanted to keep your data set private? Our model is that you want to keep it private against T colluding workers. Means that not only one node will not learn anything locally. If any T of them would collude with each other, they won't learn anything. Okay, so T is another parameter on how much protection of privacy you want to have. The idea is now you are going to pass the encoding polynomial going through your data set, as well as T other noises. These noises are the same size as your data set, okay, to completely mask your computations. And the result is that if you want to tolerate T workers, now you would need T times degree of computations more computation results. And that's the scaling that you would get.
Can I ask a question about the last 2 pages? The last one, yeah. That's the result that guarantee we can tolerate the malicious, but will there be some extra computation to find out which one is sending the wrong result?
Very good. So means typically the way you would do this is like through, syndrome decoding.
Yeah.
Right? Yeah. So through that, maybe the wrong syndromes, you can figure out which one it is. But you're not guaranteed to find all the malicious ones. If you want to do all the malicious ones, you can do it, but you have to compare the result with what they give you.
Okay.
All right, so you can use it for privacy too. Now you have your parameters K, T, A, and N. And this is like giving you a trade-off on how much a straggler you want to tolerate, how much adversaries you want to tolerate, and how much privacy you want to have. And based on that, you can design on the number of workers, or for a given number of workers, you can redesign these components. So a couple of things to highlight is, this approach, you can apply it for any polynomial computations. There are some computations that are non-polynomial. There is also very interesting recent developments on maybe instead you want to use approximations of those computations as polynomials. Okay, so there is still hope to go beyond that. And also you can see as my computations are getting more and more complex, the degree goes up. It's like my amount of computation that I need to do to get privacy would also go up. Maybe you can break that barrier, okay? And that's also an interesting question to ask. All right, so I went super slow.
Sorry, Salman, quick
Yeah.
question. What is the meaning of privacy in this setup? Like, what kind of privacy are you guaranteeing?
Very good. So the privacy guarantee is that there is zero leakage, like information theoretically private, to any T colluding workers. Means that if T of these nodes put everything together, like all the data sets that they have together, they will not learn anything about any of the data sets.
Okay. Okay.
All right. So maybe let me ask you one question, Wahida. It seems I have 9 minutes. Is that correct?
Yes, that's correct.
All right. So let me mention to you, I spend a lot of time on explaining, describing coded computing. What can you use it for? So the exciting thing is you can use it for many applications. Here I mentioned some of the things, and maybe one of them I go a little bit into detail depending on how much time I get. So the first one is, we started coded computing. At the time we started, a straggler was a big issue. And we were working on a straggler mitigation. For example, you can use it for various algorithms that you can cast them as polynomial computations, any regression with polynomial loss, PageRank type algorithms. These are just matrix multiplications iteratively, graph filtering, and you can use coded computing for those applications. We have many implementations that compared with replication approaches, you get substantial gains. I'm not gonna, talk about that. Maybe I refer you, to these papers if you are interested to take a look at them. In particular, we have one implementations for matrix multiplication in supercomputing conference. If you are interested, you can take a look there.
And questions about the regression problem.
Yeah.
Do you mean just a linear regression or any type of generalized regression method like tree-based and any other things?
So it depends on, what is your loss model. Remember, my computations should be modeled as polynomial, right?
Yeah.
So now in the context of regression, your gradient computations, the question is in what cases can you model it as polynomial? For example, any polynomial loss, you can do it. But what if you have logistic regression? In that case, right, it's going to be nonlinear. For logistic regression, we have solved that by polynomial approximation of sigmoid. But let's say maybe you look at, maybe more complicated models with ReLUs in them. We don't know how to do them effectively.
Okay.
So you can always do polynomial approximation, but the question is how much loss would you have if you have nonlinearities?
I see. Thank you.
All right, so another set of applications would be privacy-preserving distributed machine learning. There are two versions of that. What I call the first one is multi-hospitals. In a multi-hospital setting is, let's say there are 50 hospitals in New York. They have patients' record, and they want to collaborate together to come up with better models that, predicts the susceptibility of different patients for COVID. Okay, the question is, how would they collaborate with each other so that even if a fraction of them, a third of them collude, they will not learn anything about the other party's data sets? Or another version of it, let's say there are maybe thousands of Robinhood users. Robinhood wants to have a new app, a new maybe feature that allows the users to collaborate for coming up with better machine learning models for trading. And users want a guarantee that even if a third of them collude with each other, they won't learn anything about the model of the other clients, the other users. Okay, so some real problems. You want to have a strong privacies. In those cases, the benchmark, like the only schemes that give you same guarantees would be schemes based on multi-party computing. Okay, so that's the only scheme that you can use. And we have a new scheme called coded private ML, CopML. Here in this plot, again, I'm describing the result to you in 1 minute, but essentially on the x-axis, you have number of clients. On the y-axis, you have runtime. The interesting thing is that most of the existing schemes, like cryptographic schemes, as there are more and more users in the system, they become more and more complex and the time goes up, which kind of makes sense because there is going to be much more communication needed between them to do their secure multi-party computing. The interesting thing is that the coded computing approaches, well, even not only they don't go up, they get a little bit down too, because you get some parallelization gain. So we get significant gains. We have a paper next week at NeurIPS. So if you are interested, take a look there. And another application would be through federated learning. Okay, so in the federated learning, one issue is that you want to guarantee privacy of the users, and also you want to guarantee secure aggregation. Means that even the users won't learn the trained model of each other, because otherwise, you can invert the model and learn about the other users' data sets. And the issue with that is the state of the art, the complexity of it is an approach by researchers from Google that have a complexity that grows quadratically with the number of users. And with coded computing, we can get it to linear complexity. My plan was to dive deep into the federated learning part, but I'm running short out of time. Maybe I show you just one plot on what is the performance gain that you can get. Okay, and then I end the talk. All right, so the scheme that we have based on coded computing is called TurboAggregate in that context. Okay, and again, on the same plot, you have the number of users versus the total runtime. And typically in aggregation in federated learning, you want to tolerate user dropout. The red curves are the state-of-the-art schemes by Bonowitz et al. From Google. The blue curve is our TurboAggregate scheme. As you can see, the state-of-the-art schemes, their complexity grows quadratically. Here, because of the efficiency of coded computing, you have a linear overhead. And also, there is no distinction between how much dropout you are tolerating. Okay, so all of them are lumped into. So hopefully it conveys to you that coded computing is a promising approach, that you can use it for several interesting criteria that you may have in distributed computing and distributed machine learning, the issues of resiliency, security, and privacy. There is also a different version of coded computing if you want to deal with bandwidth bottleneck that I didn't talk about, but you can look at our works on the trade-off between communication and computing. I discussed for each of the applications on privacy-preserving learning and federated learning, different implementations of coded computing that you can leverage. But this is a growing field. There are many exciting problems, many exciting challenges that not all of them you can solve with coded computing. I have listed some of them in the context of federated learning, if you are interested. But in the interest of time, let me stop here, not read them for you, and take questions, more questions maybe.
Thank you. Let's thank Salman for the wonderful talk. We already asked a bunch of questions from Salman, but are there further questions?
So I have a question. So I can turn on video. So with coded computing, I think a lot of the motivation comes from machine learning, right? So in particular, training large-scale machine learning models. And these are typically iterative algorithms, right? You do many iterations to do your training. But with coded computing, it seems like we tackle each iteration individually, right? Is there any work in leveraging correlation between iteration of these iterative algorithms?
All right, so maybe I first clarify the first part. Remember, you are not tackling each iteration. The only part that you are doing individually at each iteration is the decoding part. Okay, so meaning that, let me put it maybe in the context of one of the applications that I had. All right, so let's say in this context, oh, I pushed a lot. Let's say this is the application that you had. These hospitals wanted to collaborate for training, or these Robinhood users, yeah? So the first step you would do is your data encoding. This is before the training starts. Then after that, there is no encoding anymore. The only thing that is needed is when a user, like typically in distributed training, you get the result or the gradients from loss computations from the other nodes. Before you update your model, you have to do a decoding and then apply your model updates. So that's the only thing that you have to do per iteration.
Yeah, exactly. But what about going beyond that? Maybe you could, reduce the number of workers that you need to wait for, or simplify your decoding if you can somehow use some side information. There was a paper called Substitute Decoding a while back, for example, that tried to do something like this.
Right. Good point. You can do that. I'm not sure what type of side information you are referring to in this context.
So typically the previous gradient, say.
Right. But remember, like in this context, you're asking good question. The question is, are you targeting stragglers, or are you trying to deal with privacy? In the context of stragglers, you are right. Means that you can do it, right? In the context of privacy, remember the role of the encoding and decoding is not to use more machines. It's kind of, I have to decode because everybody had injected noise, and I have to denoise it before doing the model update. That's the goal here. Okay, so in that context, I'm not seeing what would be the role of side information, but for a straggler toleration, you're absolutely right. You can use that.
Yeah, sure. No, it makes sense. I have some on the privacy part though. It does seem like there's no compatibility with sparsity. Like once you start introducing noise, you have to have dense data. Is that true?
Yes and no. I mean, the question is, would the zero parse or the sparsity pattern would leak or not? Okay, so there are some works that you can do embedding of your data set first to a lower dimension and then apply, you make it secure, right? But right now, I'm assuming that this entire vector, I have to protect it everywhere there could be a data, right? But, maybe that question is a very good question. Is a little bit tricky because most of the time you don't know what is leaking in your data set. So typically people want to protect it everywhere, right?
Yeah.
Well, in the interest of time, since Salman has a meeting starting up, I'll say we'll have to stop here. If there are further questions, please feel free to reach out to Salman. And let's thank Salman one more time for the wonderful talk.
Thank you.
And that concludes our seminar.